Alright guys. Okay, Dustin, you're on track. Today we're going to look at probability of data and percentages. So, probability multiplication rule. Melissa, I heard you say it earlier. What is that?
Probability of X times probability of Y.
Okay, so that's what it equals, right? What goes in front though? Okay, Lynn said probability of X and Y. Is it Lynn or me? Okay. Probability of X and Y. Dustin, you were reading something though. What goes on at the end of this?
X and Y are independent.
Good. X and Y are independent events. Okay. So in order for this to happen, X and Y must be independent events. Okay. So in order for that to work, X and Y must be independent events. Now, have we had any non-independent events so far that we worked with?
No.
No. Every time we've had a problem, they said they are independent events, or we asked ourselves, are these events independent? Okay. Now, when you're working on probabilities, if they don't tell you events are independent, or if they're events that you can't determine if they're independent or not, you need to assume that they are not independent. Okay? So this data sheet that I gave you, all right? This data sheet, does it say anywhere on there if the events are independent?
No.
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 So can we use this equation today?
No.
No. Okay? So this equation right here, oops, I don't want to put an asterisk. I want to put a big X next to it. I'm going to put no. Okay? Meaning, no, we can't use that equation today because we don't know if the events are independent or not.
All right.
Okay? Now, we can, however, still use the addition rule. As long as we do one thing. Okay, so there's our addition rule, right? Right? Everybody's saying, whoa, I got X and Y in there. We can't use the equation, can we? No. So where am I going to get X and Y from? The chart, right? A data table, like we're showing on the paper, is a lot like a sample space. Right, you guys remember using sample spaces? Yeah, we could use sample spaces to figure out X and Y, couldn't we? Jared, remember sample spaces? Yeah. So it's like all the probabilities for like two six-sided dice. I mean, like 1, 1, 2, 1, 1, 2, all that stuff. All right. So as long as we get our X and Y from the data, then we can still use the addition rule. Okay. We can still use the addition. So if events are not independent, or we don't know if they are, then we need to use our data table. Michael.
What?
Travis.
It was him, I swear.
I don't need theme music. Thanks for trying though. Okay. Okay. So events are not independent, or we don't know if they are. We need to use the data table to find the probability of X and Y. Okay. Now, on the worksheet I've given you, it says Mr. Branch conducted a survey of the Kellogg'sville High School staff's favorite morning beverage. The results are shown in the table below. Okay. Now, I conducted the survey via email. I sent emails out to all staff members asking what their favorite morning beverage was. They responded to me. They were only allowed to pick one. Yeah, I'm joking. I really didn't do that. Okay. I made this all up just so it would work out. This is something that I could have done though. Okay, I could have sent out an email and got people's responses. I could have used like a SurveyMonkey or another website that does that where I can collect data from. Okay. People in industry will collect surveys. And sometimes you get those annoying phone calls where someone calls up and asks, "Can I have a moment of your time, please?" Right? And they have a whole list of questions they want to ask you. Right? And you say no, or you say yes, and then you regret saying yes, and you guys, yeah, usually you say no. But sometimes when people do answer those, they get survey results like this, which will prove to be very useful, and I'll show you how as we go through today. All right. So today we have two goals. First goal is to figure out how to use this table to calculate probabilities. Okay. How to use this data right here to figure out probabilities like we're used to calculating. The second goal is how to figure out if two events are independent or not. Okay. Marcel, when I look at the data table, does it tell me if the events are not independent? You can look at your sheet. Does it say that the events are not independent? No. Does it say they're independent? No, we're inconclusive, right? So it's possible these events are independent. It's also possible these events are not independent. Okay? So that's something we're going to have to figure out as the day goes on, is if these events are independent or not. Now, would you guys think morning beverage choice and gender are independent?
Yeah, no.
Do you think gender affects morning beverage choice?
No.
No?
Yeah.
Yeah. No, it does not.
Okay, what'd you say? What'd you say, Christian?
Guys like apple.
Okay, Christian says guys like apple juice. So that means gender would affect beverage choice, wouldn't it? Okay. Guys, this is morning beverages and it's appropriate for school. Okay. Thank you. Now, last time I talked about how someone was adamant that men are supposed to like coffee in the morning.
Oh no.
Okay?
I see what girls do.
I like coffee.
But that is an example, guys, of where gender might have an effect on beverage choice in the morning. Okay? So these could be dependent events. They could depend on each other. All right? So we're going to figure that out. All right. First thing, use the table to determine the probabilities below. So we want to find the probability that if I pick one of these 30 people, okay, 30 people that participated, if I had them all in the room, okay, what's the probability that randomly I selected one person who liked coffee? Okay, so we got to use this data to figure out.
8 out of
Okay. Travis says it's 8 out of something. Where'd you get 8 out of something?
8 out of 30 because 5 females like it and 3 males like it, and there's 30.
I think you're looking at juice.
Oh yeah, it was.
Okay. So the probability people like coffee. Now I'm asking for the whole group, right?
12 out of 30.
Okay.
Well,
There are 9 males and 3 females making 12. So out of the total number of people in the group, how many like coffee? 12 out of 30. So the probability if I pick someone at random in this group that they like coffee, it's 12 out of 30.
Or 2 over 5.
Or 2/5. Nice job reducing. Okay, reducing is always a good thing. Okay. You might want to fill in your own worksheet as we go along.
Oh, okay.
Okay, now next one. Probability that they're a male and they like coffee. Okay, we have
110.
two responses, 9 out of 18 or 9 out of 30. Okay. Now, one of you that responded are thinking about what's called conditional probability. Conditional probability means I'm asking the question, if you're a male, what's the probability you like coffee? Okay. So, what do you guys think if you're a male, what's the probability you like coffee? Do you think that'd be 9 out of 18 or 9 out of 30?
9 out of 30.
Okay, that'd be 9 out of 18.
18.
If you're a male, what's the probability of coffee? That's saying only look at the males. That's saying I take all the women out of the survey and all we have left are the males. What's the probability that I pick one of those men and they like coffee?
9 out of 18.
Okay, that's what if you're male and you like coffee. That's what that one is. Okay. Now we're looking at the probability that they're a male and they like coffee. So that means I still have all 30 people in the room. What's the probability that I pick one person and they're both male and like coffee?
9
out of 30.
Okay. It's 9 out of 30 because there's 9 men that like coffee out of the group of 30. Okay. We'll get the conditional probability next week.
3/10.
Nice job. Okay.
I told
And that reduces to 3/10. You were right. Nice job, Kyler.
Thanks, Kyler.
Okay. Melissa will get the rest of it next week.
Can I skip to next week's lesson now?
I'm not ready for next week's lesson. Sorry. Now, next one, probability of pop or juice. Okay. Now I said we can still use the addition rule, right?
12 out of 30.
Right? So when I'm figuring out the probability of pop or juice, we're going to take the probability of pop plus the probability of juice, and I just use P and J instead of writing out the words. Okay? Minus the probability of pop and juice. Right? So that's our equation. Right?
That's the additional one?
That's the addition rule. Okay. Now, where do I get the probability of pop and the probability of juice?
The table.
The table. Okay? So, the probability of pop, probability of someone liking pop, do I look in males or females or look in the total?
Oh,
Total.
Total, right? Because we don't have that, we're not asking about males and females, so we're just asking about total. Okay? So 4 people total like pop, right? So this probability of pop right here is 4 out of 30. How many people like juice? 8 out of 30.
12 out of 30.
Okay. Now we have minus probability like pop and juice. Right? Now, pop and juice, those are what?
Mutually
Mutually exclusive.
exclusive.
We can't pick both, can we? Okay, we can't pick both. They only have one favorite. Right? So we know this is going to be what? 0. You can also think of it this way. When we were doing male and coffee, 9 came from where coffee and male intersected, right? Just like when we had the sample space, right? 9 is where the male column and the coffee row intersected, right? Now for pop and juice, pop's in a row, juice is in a row. Will they ever intersect? No. Okay. So that means that they'll never have an and. Okay, since they don't intersect. Right? All right. Any questions? Yes. You know that answer? What is it, Michael?
2/5.
2/5. First, let's do 8 plus 4, which is 12 out of 30.
Yeah.
Which then reduces to
I got the next one.
2/5, like Michael said. Yep, the next one, what is it?
8/15.
8/15.
Yeah.
Let's make sure.
I don't know if that's right or not.
You don't know if it's right. Okay. Let's write it over here. Does anyone else think they know the next one?
8/15.
Okay, besides Travis and Michael, because I think you guys work together.
No, I got the answer. Team Blue.
Oh, man, little cheater. Anybody else have an answer? Okay, earlier today, someone was insistent that for water and female, all they had to do was take the number of females and add to the number of people who like water.
No, because there's 2 females that like water, and you have to subtract that.
Good, man. Can't get one past you guys. All right, so there's 12 women who like water, right? 6 people who like 12 women who are, or 12 people are female. 6 people like water. Add those together, you get 18 out of 30.
Minus
Okay. Now that's incorrect because if I do that, I'm only adding the probabilities of each. I'm not worried about the overlap in mine. Right? These overlap where?
At the female and the woman.
At 2. There's 2 women who like water. Right? So we can't just add these and get our answer. We have to use the equation. Right? So the probability of water or female means you got to take the probability of water plus the probability of female minus the probability of water and female. So the probability of water was 6 out of 30. The probability of female,
12 out.
12 out of 30. The probability of water and female is, so where they overlap, 2 out of 30. So now I can add those across. 6 over 30 plus 12 over 30 makes what?
18 over 30.
18 over 30 minus 2 over 30, which is?
16 over 30.
Equals 16 over 30, which reduces to 8/15, like Michael said. Are there any questions? Any questions about that one? These probabilities seem pretty easy to figure out?
Yes, we do.
Yeah? Okay, let's try the next step then. Let's say we're gonna use our data we collected. We're gonna make predictions. Remember earlier I talked about people getting surveys and then they can use that for like marketing and information. Sorry, they can use that for marketing and other types of business aspects. Well, one of the things they can do is they can take the answers to the survey and they can use those answers to make predictions as to what a company should do next, or what type of marketing campaign they should use, who they should have in the commercials, right? So we're going to take this data and we're going to make a prediction, right? Mr. Branch's wife is throwing a baby shower for a friend, and she knows 48 women are coming. Big baby shower. Yeah. Okay. Use this data to predict how many partygoers would choose pop as their favorite drink. So, anybody know what I should do?
Take a survey.
Oh, we already have a survey. Call all their friends. So call all 48 of them.
Yeah.
But I already have a survey involving women and what beverages they like. Why can't I use this information?
They're not the same people.
But still, does Hollister call everybody and ask them what color shirt they want?
They make a bunch of them.
They just make a bunch of different colors, right?
Yeah, because people go and buy from there, but you're hosting this.
Okay. Does American Eagle call up everybody and say what color shirt you want?
Maybe.
Does Kellogg say, oh, everybody likes Captain Crunch, we need to make more of that?
Yeah.
Okay. They
They
take
take
surveys. They do. Nice. Show a jinx there. Okay. They take surveys. They don't call everybody, right? So we have a survey. We have an answer already, right? We have probabilities right here. So how can I use this data to figure out how many people like pop? Anybody know?
You
Add
just
one to every-
times that
Yeah.
by 40.
Okay, we take 48. And Travis, you said times. What do I multiply it by?
The number of people that. I don't know.
Well, that's morning though. Is your baby shower in the morning?
We'll get to that in a second, okay? So we take 48 and we multiply by what?
Number of pop.
4, 12,
The number of.
Okay. Okay, how many people like pop?
4,
4. How many of those people are female?
2.
2.
Oh, alright.
Out of how many females?
12.
12.
So 1
Okay. Only women are going to the party, right?
Oh yeah.
Right? So we should only look at the probability for females. Okay? So we take the probability of women who like pop, 2, over 12. Right? Because 2 out of 12 of the women that surveyed like pop. So we multiply 48 times 2 over 12, and we get
8.
8. So that means 8 people at the party are going to like pop. Right? 8 people are going to like pop. Does that make sense? Does that make sense?
Yeah.
Yeah. So if you are participating in one of those surveys, Mike, where people call you on the phone, right? Whatever company, let's say it's someone figuring out what type of cereal you like. Okay? If on that survey you tell me like the fruitier cereals versus the chocolatier cereals, then maybe the next cereal they'll make will be a fruity type cereal.
It'll be called Fruity Mike.
It'll be called Michael's.
Okay, fruity Michaels. All right.
Fruity Pebbles. Fruity
If the
Mike.
largest probability is
Or little critters.
people liking fruity cereals, then they'll probably go in that direction.
Jasper.
All right. Next question after this one. I know it's not on the screen because I want you guys to be able to see the work. But the next question after this one says, are you comfortable making this prediction that 8 people like pop? All right, Michael, don't shout the answer out. Okay. Are you comfortable making the prediction that 8 people like pop?
I'll bet you.
All right. So look at the work we did. Look maybe at the data and answer that question either yes or no with a reason. Are you comfortable making that prediction? All right. Make sure you include a reason. Don't just say one or the other. And please keep it to yourself, guys. We'll have a moment to share.
What time are baby showers?
Depends.
In real life?
Depends.
Man, I used to respond to it.
You can have them in like a brunch baby shower where it happens at like 10 in the morning. You could have an evening baby shower where it happens like 8 at night. You could have one in the middle of the day. It all depends on the type of baby shower. Depends on the theme.
I used to respond.
Although I've never been to one. If they put a baby shower aficionado right now.
Did your wife have to help you out with that question?
Yes, she does. It's her idea.
Really?
I was just trying to think of something that only women would go to. I thought there's not couples baby showers. I've never been to one.
Bachelor party.
All right.
You use the condoms.
That has negative outcomes. Though, sometimes. All right.
Yeah, it does.
Are we comfortable making this prediction?
No.
Who says yes? Yes? Jared, why do you say yes? Okay, because we did the equation. Where do we get the 2 out of 12? For our table for only what? Females, right? So doesn't that seem to fit?
There's baby.
Okay. So yes, because we only use the probabilities for females we got from our survey, right? Anyone else say yes? Okay. Anybody say no? Michael, why do you say no?
Because we don't know what time this is taking place, and this is just from the morning. But maybe people will want to drink pop more in the afternoon or at nighttime.
Okay.
In the morning.
Okay. Sounds good. So we looked at morning beverages in the survey, right? The baby shower might not happen in the morning. Okay. Everyone else say no. Okay. Melissa, why'd you say no?
Because the survey we used to figure this out does not pertain to our situation.
Okay, why do you think that?
Thanks, big word.
Because it's, I hate drinking coffee in the morning, but I might like drinking it later on, and it doesn't say when the baby shower is. So.
Okay, so it might not fit in that situation. Okay, I gotcha. Jared, do you have anything else?
I said people tend to drink coffee more in the morning, so I think later on people will drink it.
Okay. So it kind of all depends on the time. Whereas in the survey we did favorite morning beverage, whereas in the afternoon or in the baby shower we don't know if it's an afternoon, a night, or a morning baby shower, right? If it was a morning baby shower, this might work, right? Right? We don't know that for sure. Okay. Another argument someone made earlier for saying no is that this survey was high school staff, right? Okay. All 48 people going might not be teachers or other high school staff, right? So they might like different things. Okay, that's something someone made earlier too. All right, good. I would say either yes or no could be correct depending on how you justify. There are certainly more arguments for no than there are for yes, but either one, depending on justification, could be useful. Okay. Any questions? All right, so we got one goal accomplished for the day. The second goal was to figure out how to determine if events are independent or not. Now, I need to scroll down, so make sure you keep your sheet out that has a table on it because we're going to need to use that table. All right, so second goal of the day was to determine if events are independent. Now, to do so, we're going to need to use the multiplication rule. So it says the multiplication rule states that x and y are independent events if the probability of x and y equals what? Anybody know?
0,
No.
30,
No.
8,
No.
12,
In general.
1, 0.
1. Px minus py.
Okay. So the multiplication rule states that x and y are independent events if the probability of x and y equals probability of x times probability of y. Right? Same multiplication rule we learned a couple days ago. Right? So now we're going to use this to determine if two events, gentlemen, please stop whistling, to determine if two events are independent or not. Right? So the two events I'm worried about are being female and liking juice. We want to know if those events are independent. Okay? If they're independent, then what's true about being female and liking juice and the probability of Thank you, Callie. Okay. Now, if these events are independent, all right, then being female and liking juice will equal the probability of being female times the probability of juice. Okay, if they're independent. Okay, so if this is the case, then the events are independent. Okay, if that's the case, the events are independent. Now, how do I figure out if that's the case? Where can I find these probabilities?
In the table.
In the table. So using the table we were using earlier, you guys can find the probability of women who like juice, right? Right? We look at the juice column, or sorry, the juice row and the female column. You see where they overlap, and what do you get?
5.
5. So that means 5 out of 30 are both female and like juice.
1/6.
Right? Reduces to 1/6. Okay? Make sure you leave the 1/6 off there right now, Michael. Stay with 5 out of 30, okay?
Okay.
Now, what's the probability they're female from our table?
5 out of 12.
5 out of 12. What's the probability of liking juice? Oh, wait, it's not 5 out of 12.
That's 12 out of 30.
Travis.
Just kidding.
12 out of 30.
12 out of 30, thank you.
That's what I meant.
Hey, I got you.
Travis.
Okay, nice job, Travis. So, probability they're female is 12 out of 30. What's the probability they like juice?
That's 5.
5.
Okay, it's everybody though, right? So the probability they like juice is 8 out of
30.
30. So, what's 12 out of 30 times 8 over 30? Can you use your calculator? So do 12 over 30 times 8 over 30.
Bottom number's 9.
8 out of 30.
Okay. This ends up being 96 over 900. What that reduces to 8 over 75. Now, does 8 over 75 equal 5 over 30?
No.
You sure?
Yeah, it does.
It does.
Wait,
Alright.
no, it doesn't. Because
Okay.
double 5 over 30 is 1060.
Okay, the fractions aren't equal, are they?
No.
Right? Michael's kind of going around looking at decimals. I know I'm getting a little further down the page, so you guys can move over here if you want to. As decimals, okay, this is 0.17 approximately, 0.16 repeating. Okay, 8 out of 75 is approximately 0.11. Are those close enough?
Yeah.
No.
No, those are not close enough. Okay, so these are not equal. So what does that tell us about the events? They're not independent. So all these equal signs end up being not equal. Okay? And since they're not equal, actually I want to make that one not equal. Since they're not equal right here, that means the events are not independent. Because it's not equal. Alright? Now, if those were equal, then we could say they're independent. What if, for example, and this is just purely hypothetical, let's say I got 0.1666, and for the other one I got 0.1663. Would that be close enough? Yeah, that'd be close enough. What about for one I got 0.166, Travis?
Yeah.
And for the other one I got 0.170.
Yes.
Would that be close enough? Would that be close enough?
Yeah.
Yeah. I'll give you another 6, Jared. That's a long enough pull. Okay. Alright. Would those be close enough? Yeah. What if I had one that was 0.66666 and one was 0.135? No, a little too far apart, right? If they round to about the same number, then they're probably close enough to call independent. Now, why might that be important to a marketing executive? Someone who makes ad campaigns. Why would knowing that being a female and liking juice are not independent events? Okay, we know who to target, right? If liking juice is dependent upon gender, right? Then we can target that gender, right? If, let's say, for example, and this is purely hypothetical because I made up the data, let's say that women like juice more than men, okay? Showing that they're not independent, that might indicate that. So then when we make our television campaigns, what are we going to do?
Advertise to women.
Advertise to women, right? We're going to have women in the commercial drinking juice, right? Does that make sense? Right. So the information we're getting today with probability from data is useful to people who make like campaigns or make marketing campaigns. Presidents who make campaign ads, same thing. They do surveys, but instead of about what juice or drink you like, they look at like issues like education reform, okay? Whether we should improve roads, whether we should build bridges to places, all right? And then based on those, they make certain campaign ads, all right? So this probability idea is getting probability from data is a concept that's used an awful lot in the real world, all right? All right, any questions? No questions? All right, versus try on your page. I'd like you to try those on your own, okay? That is it.
Do the other side of the